So, somewhere I read there was this running joke for engineering students where they like to approximate things. And among many things, engineering people like to make fun of engineering for approximating e to be 3 and then approximating pi to be 3 as well because they just like rounding. Also, there's also some jokes that they um, write this sine of x is equal to x, so they use this approximation in their calculations. And this last one, sine of x is equal to x, actually is a Taylor series, or one part of a Taylor series that we're going to start looking at. And Taylor series is this idea that a lot of people don't appreciate because it's just a formula that people will just see like, oh, you have to memorize this formula to know Taylor series, but there's actually a lot more to what Taylor series tries to do. It sets the stage for higher level math and higher level physical sciences and even science in general. In higher level math, you actually use Taylor series to solve differential equations because some differential equations are impossible to solve without Taylor series. And then in physics and engineering, if you end up going through those fields, you're going to be using Taylor series to help you approximate things. So this is where that joke comes in. Engineering likes to approximate things, and this is a Taylor series right here, or just a first order Taylor series, and we'll learn exactly what I mean by that. But let's take a look at a graph of sine first, and see what I'm talking about with Taylor series. So here I have a graph of sine of x, as you can see by its waviness, right? It starts at 0 and it has this peak at pi over 2. It's kind of weird that it says pi over 2, but it is not actually sine of x. It's actually a polynomial, and if I zoom out you'll see what polynomial starts to look like. So it looks like sine of x, and it actually has this graphing that says it's pi over 2. But if we zoom out, we see it is actually a polynomial of some sort. But what exact polynomial starts to look like sine at the beginning and just doesn't actually get to sine at the end behaviors? Well, it is this function, and it looks like it's a bunch of terms, but see that there's a pattern here. And there's actually, I've written a lot of terms here, all the way to about 29, I think, x to the 29th. And see that the pattern is that it's alternating signs, it's odd numbers, and then there's a factorial, which is kind of weird. Why is there a factorial appearing in polynomials? And how does this all relate to sine of x? If I were to actually type in sine of x, and I zoom in close to this point 0, notice that this curve actually pretty much exactly matches sine of x. If I just take it away and reappear it, it's basically the exact same thing, but as soon as I start getting away from the center, is what we'll learn why I call it a center, it starts to change, or like diverge from it, because of course polynomials have to end up somewhere. And I can actually make this better by adding more terms. So I know the pattern, so if I keep adding these terms, it's going to start looking better the more terms I add. So I'll just add a few more, so you'll see how it gets better every single time. And this pattern is actually very exact. If I take, for example, if I change this to 36 or 37, for example, it starts to not be able to match this. Look, if I just take away the factorial and put 37 or 35 here, look how it just doesn't even look like sine anymore. But as soon as I add that factorial, it looks like sine of x much better. So how do I know this pattern is this, right? That's what that's what Taylor series actually shows. Taylor series is this idea that any function you want, any of them, like sine of x, cosine, arcsine, e to the x, natural logs, can be written in terms of a polynomial or an infinite string of polynomials, but it's also used to approximate things. So that joke with engineering students, if I were to, let me just get rid of this really quickly. This engineering joke is that sine of x is actually equal to x. And notice that if we zoom in really close to 0, it kind of looks exactly like x, and this is an approximation. So that's the second use of Taylor series, is that it helps us approximate values that we do not know the value of. For example, if I wanted to find the sine of 0.01, which is really close to 0.01, Notice that 0.01, if I just typed it here, is very close to this value. If we rounded to the nearest hundredth, it would be exactly this. So this approximation joke actually shows why it's a joke. It's a joke that people make because they make fun of engineering for being approximators instead of exact values. So that I found that pretty interesting. So now we bring it to the question of how do we actually know what the pattern is? How did I know that the pattern was this? So let's talk about that. So here's what I have. I have sine of x is equal to this, which is what we saw earlier, and this will go on to infinity, repeating this pattern over and over. This is exactly what sine is equal to if this pattern were to go into infinity, but if we were to stop it somewhere, it's going to change into an about symbol, like about this much. It's an approximation. But I want to show you why this works the way it does. The reason why it works the way it does is that sine of x and this polynomial right here have matching first, second, third, fourth derivatives, and so on. So, and matching derivatives. And let's see what happens. If I took the derivative of both sides, so this would be cosine, and I took the derivative of this, let's say they're equal for now, 1 minus 3x squared divided by 3 factorial plus 5x to the fourth minus 5 factorial minus 7x to the sixth, 7 factorial. Things happen. It has matching derivatives, and what do I mean by that? If we were to plug in a number, for example, cosine of 0, since this is the derivative, f prime of 0, if I were to plug in 0 here, it's equal to 1, right? Cosine of 0 is 1. And then let's see if that pattern continues on. It has matching second derivatives. So the derivative of cosine is negative sine. So that's equal to, when we just compute this really quickly, it's negative 6x over 3 factorial plus stuff, right? 20x to the third, 5 factorial, and then negative 42x to the fifth, 7 factorial. So I'm going to scroll down from here. And if we were to plug in a number 0, again, sine of 0, negative sine of 0 to be exact, negative sine of 0 is 0. And this thing, since every term has a 0, is also 0, because 0 is equal to 0. So they have matching derivatives. So then the question, I guess, appears, why is it going to be factorial? Why can't it be something else? So let's answer that question. Let me just erase a couple of lines here. Let's do it from here. Notice that if I simplify this expression, it's actually going to be appearing something like this. I'm just going to do the first two terms after the ones, just to show you what I'm talking about. Notice that these will cancel out with this, and we're left with 2 factorial instead of 3 factorial. When we took the derivative, the power has to go down, and since the power matches exactly what the factorial is, it will cancel out and be 2 factorial. And if we were to repeat doing the power rule over and over, the factorial just starts to go away. So this factorial here actually stops, or kind of like balances out the repeated use of the power rule. So that's the idea of the factorial appearing here. So now this is I guess, the reason why there's factorial appearing, and then we can also see sine in this polynomial here has a lot of the same behavior. Sine is an odd function, this is an odd function. What else can we know about this? That seems about right. They have matching derivatives, which is pretty much the key of what Taylor series actually tries to do. So Taylor series is, here, let me write it down. Taylor series models any function as polynomials. And by any function, I mean sine of x, like those weird functions that are not polynomials. Even it can model polynomials as polynomials, which is kind of interesting to look at. But any function at all, any function you want, by matching its derivatives. So what I did in that graphing part of this video is that I matched the derivatives, and I just continued matching its first, second, third, fourth, all the way to its 29th derivative. And if I do that, I get a polynomial that has the same exact behavior as sine of x. And that's how I got into this pattern, and I noticed there was a pattern emerging. So that's the idea of what I'm trying to, I guess, try to convey with Taylor series, is that Taylor series models any function as a polynomial by matching its derivative, and with that, we can use it to approximate. How does a calculator know exactly what sine of 5 is, right? What is sine of 5? They use a Taylor series because it's so much easier to plug in numbers into a polynomial than knowing the exact value of sine, right? Sine of 5 is kind of hard to know, but if I would say, given this polynomial, can you evaluate it at x equals 5? That would be much easier, but it'll also take a lot of work, but it's still easier than finding what sine of 5 is without a calculator. So we can use it to approximate functions. And the more terms we have, the better. So this is the introduction to Taylor series. Hopefully you gain some sort of appreciation of this joke. I don't know. If you ever see jokes about engineering, or just even search up engineering jokes, they like to make fun of engineering being approximators, and this is one example of an approximation they make, and this is a Taylor series, or the first term of a Taylor series, in fact. But you see how Taylor series helps us approximate, because we don't know values of sine automatically, but we do know values of polynomials that we know of, and we can calculate that much easier. That's exactly what a calculator does, but they do it with a lot more terms to get in more precise values, because the more terms we have, the better. So hopefully you gained an appreciation of what Taylor series tries to do. I kind of find this fact very cool, because any function you want can be modeled by a polynomial just by looking at the calculus of the curve or calculus of the function, and just matching certain features of it can lead you to a Taylor series of any function.